Okay, this lecture is going to cover some topics from the electric field chapter that we're currently studying. And primarily, this particular topic will be the superposition of electric fields. Part 1. This is for discrete charges. And a discrete charge distribution is when the charges themselves are point charges and they are combined together to form a combination like a line or a triangle or a square or a circle where the individual pieces are still point charges. So a um, the superposition will occur as the superposition or the sum of the individual electric fields due to the point charges. Okay, let's take a look at a situation where we have two charges and they are both going to be contributing to the electric field at point P. The two charges are separated by a distance d and are on a line with each other. And then the point that we're interested in is going to be a distance d over 2 away from the other charge. Let's say that the black charge here is going to be negative and the red charge is going to be positive. So let's go ahead and find the electric field at point P. The way I would approach this problem is I would individually draw the electric field vectors for my two charges. And electric field vectors for a point charge always point either directly toward or directly away from their associated point charge. So for my charge here on the left, my negative q, the black charge, at point P, I'm going to draw a dotted line that connects point P with the charge. Now I know that the electric field must follow that dotted line. So at this point, starting at the point where I'm interested in, I would draw a line, and since this is a negative charge, I'm going to draw a line toward the negative charge. That's my electric field vector for the black charge. Now the electric field vector from the red charge, since the electric field, the red charge is positive, it's going to again be connected along the dotted line that connects the point charge with the point. So I'm going to draw my electric field vector going away because we know the rule that electric fields point away from positive charges and toward negative charges. At this point, I now have a free body diagram problem. And if I wanted to, I could redraw this as a free body diagram with my force downward, or my electric field downward, E, and I'll call this E sub plus to represent the positive electric field from the positive particle. And I'm going to draw my electric field vector up to the left here as my E minus, meaning the electric field due to the negative charge. And so to find the net electric field, I would have to add those two vectors together. So let's go ahead and calculate what the magnitude of each of those vectors is. E minus is going to equal the electric field due to the point charge. So I'm going to use the electric field of a point charge. And its charge minus Q over R squared. But I need to figure out what R is. And R is the distance from the point I'm interested in, that would be the point here, point P, to the charge itself, this. So it's the distance across that diagonal. This is my R, across here like this. So I need to figure out what that is. Well, I know that this thing forms a right triangle. So I know that d squared plus d over 2 squared must equal R squared. So my electric field from the negative has a magnitude of 1 over 4 pi epsilon 0 q over d squared plus d over 2 squared. Now I could simplify that if I wanted to. Now I can do the same thing for my electric field due to the positive charge. Electric field due to the positive charge is going to equal 1 over 4 pi epsilon 0 times q over r squared. It's the exact same representation because they're both point charges. And I'm now going to put in the distance, in this case, 1 over 4 pi epsilon 0 positive q over, and r in this case is the distance d over 2. So this is d over 2 squared. So there's my two magnitudes. I have my magnitude for my electric field due to the positive charge in this diagram, and I have my electric field due to the negative charge in this diagram. So to get the total electric field, I have to add those together. It's the sum of the positive vector plus the negative vector. And since they don't point the same direction, I can't just add them together. So now our problem has turned into a vector sum problem. And we know that to find the sum of vectors, the easiest way to do this addition problem is by components. So we need to break those other fields into their x and y components. So E plus is an easy one. I can write that vector as 1 over 4 pi epsilon 0 q over d squared. The 2 gets squared and becomes a 4 on top. The 4's cancel out. And so I get this expression. And that points in the negative j hat direction because it's pointed downward. So this field, the red arrow here, is pointed downward. That's negative j. There is no I component for that particular one because it doesn't point at all to the left or right. Now, in the case of the black vector, the E minus vector is going to have both x and y components. So it's going to be the magnitude of E minus, and I'm not going to write out this whole thing. This entire expression that I'm circling here, that is the magnitude of E minus. So this is going to be the magnitude of E minus times now we need to pick an angle. So I'm going to go ahead and take that drawing and redraw that black vector drawing over here to the left a little bit. So there's my vector E minus. So I need to turn that into a right triangle. So I'm going to go straight across and straight up and down. There's my right triangle. So I'm going to go ahead and call this interior angle theta, which means that the x component is going to be the magnitude, E minus, that should be a minus, times the cosine of theta. And that points in the I hat direction. And because I realize that's going to go to the left, I'm going to put a minus sign in front of it. And then I'm going to add that to my vertical component, my y. So that's going to be, again, E minus. And this time it's going to be sine of theta because that's the vertical side of that triangle I just drew. And that'll be j hat. So now I can figure out what sine and cosine are from this triangle. Well, if this angle is theta, then this interior angle is also theta. And you can see that from my diagram. And so I can now use the big triangle to find out what sine and cosine is. So sine of theta is going to be equal opposite, that's d over 2, divided by the length of the hypotenuse, which we know is the square root of d squared plus d over 2 squared. And cosine of theta is going to equal adjacent, which would be d over the square root of d squared plus d over 2 squared. So my expression is going to get pretty complicated here. I'm going to rewrite this as E minus vector is equal to 1 over 4 pi epsilon 0 times q over d squared plus d over 2 squared. That's my magnitude of E minus. That was from this circled expression up above. And then I'm going to multiply that times the cosine of theta. Cosine of theta was d over d squared plus d over 2 squared, square root, and that must be going in the I hat direction, plus that same expression, 1 over 4 pi epsilon 0 q over d squared plus d over 2 squared times sine, which is going to be d over 2 times the square root of d squared plus d over 2 squared j hat. Now I have things in terms of components, and I can actually add these together. So I can only add like components. So that means I could add this term, the e plus term, can be added together with the j hat term from e minus. But I can't add it to the I hat term because they don't have an I hat in common. So I can get my final answer, E vector is equal to 1 over 4 pi epsilon 0, and we'll put a Q. We're going to do some factoring while I'm at it. So that's going to be common to every single term. Times, now I need the I hat terms. So this is going to be d over d squared plus d over 2 squared to the 3 halves I hat plus, now I need the e minus term, or I need the j hat terms. So I'm going to end up with a 4 over d squared. That should be a minus. That's from the e plus term above. So that's where that term came from. And then the j hat term from here, which would be plus q, plus d over 2 d squared plus d over 2 squared to the 3 halves j hat. And there's my answer. And you may say, boy, that is really ugly and really complicated. It's true, the algebra got ugly and the solution got ugly, but the actual process is going to be very similar for any arrangement of charges. You're going to add up the individual vectors from each individual charge in your arrangement to find your sum total vector. It's called the principle of superposition, and so your knowledge of how to add vectors becomes very important.